तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will continue to, we were looking at the last class, that is the general nonlinear models and its implementation. So we saw that a nonlinear function, if you want to fit the nonlinear function to a set of data points given to you, then we would declare, as we have done for the case of a linear function, a chi-square, which is the difference between the function values with the data points with the data given to you, the difference squared divided by sigma I square. That is a function, the nonlinear function. By that we mean nonlinear in the parameters a. So we saw, and also in the parameters x. We saw that earlier, when this function is nonlinear in parameters in the variable x, but not in parameter a, then we could still use a linear fit. And our idea here was to find out this nonlinear parameters a by minimizing this chi-square. That is where we stopped in the last lecture. So we said that we have a set of parameters ai's, okay, that is ai, a1 to an, and which you would represent by a column vector a, and then we have a chi-squared of a. And so instead of straight away minimizing this and trying to find the solution to that set of nonlinear equations, which we can do if you write down the chi-squared and if you write the full functional form, we could differentiate chi-squared with each of these ai's and get a set of equations, nonlinear equations of course, because f is nonlinear now, and you could find the solution to the set of a couple nonlinear equations. That is hard to do. So one method of doing that in some way is to actually do an iterative procedure. Instead of doing a straightforward solution, we do a iterative procedure. That is, we would assume a value of a or set of values for all the a's, that is called vector a0 now, that is a0 is a01, a02 up to a0n, where n is the number of parameters, and then we would expand the chi-squared around that value, the chi-square of a0 minus the Taylor expansion. So now this is because these a's are now a column vector, so you have d is now a vector containing all the derivatives of chi-square with respect to a case. So that is with respect to a's, that is the vector d, and then you have a matrix d, which is a second derivative, which is the second derivative of chi-square with respect to two values a, k and a, j. So that is a Taylor expansion for chi-square. So what the idea here is that if a0 is a good assumption for the solution of this minimization thing, and then if I expand chi-squared around that a0, this derivative should be very small, because if its a0s were actual minima, then all the derivatives should vanish, and if it is not an actual minima and if it is close to the minima, then this will be a small value, so I can actually expand it around that point. And also by expanding this way, I can go to the actual minima. So that was the idea, right? So we go to the, by expanding chi-squared around the values which we assume to start with, for a0 we can go to the actual minima. So that means this chi squared a, we assume here what we get the chi squared a is actually the actual minima, that is the derivative of chi squared a with respect to a, it should be 0. So to summarize, we are not writing down the chi squared here in this way, we are not minimizing these chi squared straight away with respect to a and finding the solution. Instead of that, we assume a set of values of a naught, values for a are called a naught, expand chi squared around that a naught, and then say that this del new chi squared, that is the value delta a away from a naught, is the actual minima. So then I find the derivative of this chi squared with respect to a and equate that to 0 and solve for delta a, and thus go to the correct minimum. So that's what we were doing, and the delta a thus obtained and from which we can get the a. The delta a thus obtained may not be the correct one again, because we are going to say that we are going to first of all ignore higher terms here in the Taylor expansion. We kept only up to the second derivative. So that is going to be an assumption. So what the delta a we are going to get from the solution will still not be a correct solution. Right. So what we have done in this process is to minimize to reduce this nonlinear problem, that is a set of nonlinear equations which we would get if I differentiate this with respect to a, to a set of linear equations in delta a to solve. Okay. But this delta set of linear equations which you obtain are also because of an approximation in the Taylor expansion we made. So the a naught, the new a value we get may not be the actual minima of chi squared. It will not, this new set of a's may not minimize chi squared correctly. So what do we do now? We take that as a new a naught and go back and then continue this loop. That's what we saw, and we saw a sample program which implements this too. And we said that this the d's elements of d which I call alpha kl here, and the elements of this d which I call beta here, and this is the first derivatives and the second derivatives, and these elements again had to be determined as a second derivative of the chi squared and the first derivative of the chi squared. So we'll again assume the second derivative of the chi squared, which has actually we saw yesterday were two terms, that is a second derivative of the function f with respect to a and b, a, k and al, and the product of the first derivatives of chi squared with respect to a and with respect to al. So we'll again make an assumption in that we will not actually do a second derivative of the function, we just use the product of the two first derivatives as the elements of this. That's something which we saw yesterday. And with that we can actually solve for, we will make that assumption because anyway we have making another assumption that the Taylor expansion can be cut off beyond the second derivative, and we are doing an iterative scheme, and after all the correct solution should be something which would make the first derivative go to 0. So we could afford to make this assumption and then solve for this thing. So again the problem was that if you not make the correct initial assumption, then we may not get the go to the correct solution. That is, again we are making an assumption here that we make an approximation for a and as a naught, and we do this iterative scheme, and we kind of hope that we go to the correct minima, that is the chi square will get minimized, or this iterative scheme will lead to a which would give me the first derivative of 0 or a minimum in the chi square. The chi square will reduce and go to a minimum. That's our assumption is. But that may not be true if we choose a delta a value which is far away from the minimum of chi square. Okay, if you choose a new value, the value a was far away from the values of chi square, then the new value we obtain may not be guaranteed to be smaller than the previous one, right? So that's something which can occur. In that kind of situation, instead of solving an equation using the second derivatives in this form, one would like to actually go to either a new assumption for a naught, okay, or multiply this a naught with a constant and go to a new value. So that's what we studied. So one possibility of going to a new set of a's, or we could multiply the set of a's with a constant value and then go to a new value. That is the two possibilities. And the second one, where we take the delta a1, we take the constant multiplied by d1. That's we go to a new set of values which are constant terms multiplied by the d1 is now the element this is the first derivative. Okay, so if you change the delta a1, instead of solving that matrix times d1, we would simply multiply it by a constant, the first derivative, and go to a delta a1. So if you look at this, it's saying that basically saying that in our Taylor expansion we would be even ignore the second term, okay, and we'll just keep this term, right? That's what we are trying to say. Okay, so we will just go to a new delta a value by simply multiplying the present delta a value by the present d value, the derivative, by a constant. Okay, that's what we're going to do. So then the question arises that what is the value of a which you would choose? What would the constant value which you would choose? So then we say that since the a is in the function could have different scales or different dimensions, so we cannot take the same constant for all the d values. So the correct thing to do would be to take the second derivative in the Hessian, only the diagonal elements, because they are, if you look at the diagonal elements of this matrix delta KL, okay, so which is now will be del f by del AK into del f by del AL. So that is what this DKL would be, this matrix, right. So the diagonal elements of that is del f by del K into del f by del K. So that would have the correct scale for each of the A's. So we could use instead of using the full matrix which obtained from the second derivative, we could modify that matrix and give the diagonal elements a little more weightage. So that is the idea behind this Levenberg-Marquardt method. Okay, so that is what we would implement here. Okay, so that is to say that we will take the matrix elements and we will take the diagonal elements and multiply it by a quantity called 1 plus lambda, okay, and then get the new diagonal element values. So we will modify only the diagonal elements. The off diagonal elements when I not equal to j is left as it is in this matrix. Remember, this matrix is actually the second derivative of the function of the chi-square, that is approximated as the product of the first derivative of the function f, which we want to fit in. So now then what we would say is that if we make an assumption a naught, and in the first step if the chi-square, the new chi-square we obtain from the new a values, okay, obtained by solving that linear equation, is less than the chi-square in the previous step, then we will continue with this matrix. Okay. Or if it is greater than, that is if we are going in the opposite direction to the minima, that is we are not going down the valley in chi-square, but we are going up, and in that case what we would do is we would increase the value of lambda and thus give more weightage to the diagonal elements. Okay, so that is what we would like to implement. Okay, so that is in short the program for a nonlinear fit will now look like this. We will choose apart from the a assumptions a moderate value for lambda, okay, which is the weightage which are going to give for the diagonal elements, and then we will compute the matrices D and the D, that is the first derivative and the second derivative, the Hessian matrix, and we will solve the equation 1, which is the equation which says that D times delta A is the little d, and evaluate the matrix A. So we will solve those set of linear equations and evaluate the new value of A, that is, and we would evaluate chi-squared at the new value at a naught plus delta A, and then we will compare this chi-square with the old chi-square which we had at chi-square as a naught or chi-squared, and then we would see if this chi-square is increasing, then that is if chi-squared, the new chi-squared value is greater than the old chi-squared, then we would increase lambda by a factor of 10. That is, this lambda is now increased by a factor of 10. But if it is less than, the new chi-square is less than old chi-square, then we will decrease it by a factor of 10. And eventually the lambda could go to 0, and so the diagonal elements will be just, since it is multiplied by 1 plus lambda, it will remain as the Hessian, the true Hessian. So that's the idea here, that we choose a moderate value of lambda and we'll increase the lambda if it is going away from the minima, and it will decrease the lambda if it is going towards the minima. And then we go back to the step 2 and repeat the procedure till the d is small enough. That is, we'll go back here and then again continue this thing until the first derivatives are small enough, the tolerance value is specified by us. Okay. Remember, this is an important procedure in numerical methods, because it's not only just to fit a nonlinear function, we could also use this for any nonlinear function minimization. So this is a general technique for minimizing a nonlinear function, a nonlinear function of many variables. You could use this particular method, this Levenberg method, to minimize that function with respect to those parameters. That's what we will be looking at. So we'll now see an implementation of this scheme, this lambda scheme, which is important. Okay. And before we go into the more general ideas of solving a set of linear equations, remember that we have to actually solve this equation if you want to get the A's. Okay, we have to set this. We have to solve a set of linear equations. That is this particular equation, right? Or we have to solve, basically saying that to get the A nu, we have to do this quantity. Okay, that's what our idea is. Okay, and this we can do very simply for a case, because we have to find the D inverse. We can simply do this in the case of a 2 by 2 matrix. That is, if the number of parameters are only 2, then we can very easily do this. That's what we would be we will check as a program just now. Okay, so here is a program for that. Okay, which part of it which we saw in the last class. That is, we had the data points stored in the x and y, and we had a matrix. Now it's just a 2 by 2 matrix. Okay, and we have the first derivatives, the second derivative of Hessian here, and the first derivatives in this matrix. And we have only 2 parameters to determine A1 and A2. So all of them are floating points, and I've declared them as floating points. Okay, so this is an array for x and y with xi and yi. Okay, here is the second derivative matrix, and here is the first derivatives, and here are the 2 parameters A1 and A2 determined. And then we need to store this chi squared and chi square old, because every time we change the A, we go through one step in the iteration. We need to store the old chi square value, because we want to compare to change the lambda. So we will also have to have a lambda, which I call L here. Okay, and this would be the determinant of this D matrix, which we would need to find its inverse. Okay, so we'll open a file, and then using this file pointer, which I've declared as here, file pointer fp1, and I will use this to, you should be now very familiar with this. That is, we'll use to open the file using the fopen command, and then it's for reading that file, so R. Okay, and I will read using this while statement, while till the end of file statement. Okay, to read all the elements in that file, and we'll just compute the number of points in that, number of lines in that file, which is now nonlinear dot data. Okay, so having obtained that data into xi and yi, okay, remember the way to read it is use this ampersand sign, so it's pointing to that particular memory location, and we read off that xi and yi. And once you have that, now once you have the data points been read off, then you now need the initial guess for the A1 and A2, and this is a simple program which has only 2 functions, 2 values, and the functional form we are going to fit is this one, that is exponential A1 x of I plus 3 times exponential A2 x of I. So that's my f of x I, exponential A1 x of I plus 3 times A1 x of I. That's my functional form. So it's a very simple function, only 2 parameters A1 and A2 to determine. Okay, so that we can do this, we can find the inverse pretty easily. Okay, so now we need an initial guess for A1 and A2, which you have to type in. So they will read it off using this scanf function. Now just remember, this is scanf function, while this was reading from a file using fscanf. So this is reading from the terminal, that is on the screen. So that is, yeah, and it will read both A1 and A2, both are floating points. And I will set chi square equal to 0 and then go through all the points going from 0 to n. To compute the 0 to n is a number of data points which we have, and we will compute that and obtain the chi squared value. Right. So we are computing that basically f minus y, that's f of xi is exponential a1 xi plus 3 times exponential a2 of xi minus y of I, and the product of that, the square of that, so I multiplied it twice, okay, so that it's the product of this 2 again. So it's basically exponential a of xi plus 3 times exponential a2 of xi minus y of I whole square, yi whole square. Okay, that's what my chi square is. Sigma here is divided by sigma I squared, which we put it equal to 1. So sigma I square is 1 because all data points are equally reliable. That's what the assumption here is. Okay, and then I now need to compute the matrix elements. That is the next element, the next part of the program, and I need to do this till my first derivatives, which are stored in the d, that d0 and d1 goes to 0. So until this first derivatives are 0, that means I put a tolerance of 0.01 here. Okay, till this elements of the d vector, that is d of 0 and d of 1, the absolute value of that is mod of that d of 0 and d of 1, sum of these two. So that's I define as the error, or the, and that should be less than my tolerance, which is 0.01. So if it is less than this, then it will stop program. So till that it will continue the iteration. So I initialize my d of 0 and d of 1 to 1 and lambda to 1, and then I go back here. Okay, so okay, I can do that here. So I do the d of 0 0. All the initialization is done here. Sorry, all the initialization of the vectors are done here, and then I actually compute. Right, so I compute the second derivative. Now, like you can see, the second derivative is computed as the product of the two first derivatives of the function. So the first derivative with respect to a1 is x of I exponential a1 xi, and the first derivative with respect to a1 again. So because this is d0 0, so this is a product of the first derivative with respect to a1. Now this is a diagonal element of the matrix. It is d0 0. It's a diagonal element of my second derivative matrix. So that has to be multiplied by 1 plus lambda, which is 1 plus L. Okay. So that is doing exactly what we were saying here. So we will use this this idea that all the diagonal elements will be multiplied by 1 plus lambda. So I multiply by 1 plus lambda here, and this is an off diagonal element, so that has not been multiplied by lambda. So just the same as the product of the two first derivatives, exponential a1 xi and exponential a2 xi into now 3 times x of I into 2 times x of I. So that is that's an off diagonal element. Okay, everything has a 2 because we have absorbed 1 2 into this derivative, second derivative here. Okay, so now then we have the D matrices, which are y of I minus that is the function, the y of I minus the function times the derivative of the function. So that is what has been given here. Okay, so that has been put in here, and then we have the, so the d of 0 and d of 1 has been computed. Okay, so we saw this yesterday again. So there is no change in this from the previous simple iteration scheme. This change comes here only in the diagonal elements where you put in a 1 plus lambda. Okay. And then now I just find the, this step is actually to find the, this step is just to find the determinant. Okay, so that is the determinant of this function of this matrix D. Okay, and then I am just printing out the values of all the elements here, matrix elements here. Okay, now this is a solution of the equation, that is the, this is the inverse of the matrix, right? So the inverse of the matrix times D, that's what this particular expression is. Okay, so the inverse of the D matrix multiplied by D minus A1 is my new A1 value. Okay. So new A1 and A2 so thus obtained. Okay, I can compute now the new chi-square value. Okay, now I have the new A1 and A2. So I store the old chi-square which I had into a thing called chi-square old, and I set chi-square equal to 0 again, and compute the new chi-squared here. So this is all simple and same as what we've been doing before. So I compute the chi-square again here, and now I say that if chi-squared new, that is chi-squared, is greater than or equal to old chi-square, then I will increase the L by a factor of 10. Okay. Now on the other hand, if it is less, then I will reduce it by a factor of 10, that is multiply it by 0.1. So that's the idea. Okay, then I will print out the chi-squared, the standard error, and the chi-square and the standard error. We print out that. Okay. That's what we are going to do. Okay, in this program. Okay, so we can run this program and then we can see what we actually get. So here again I am printing out in this point I am printing out the A1 and once I get the new A1 and A2 values, I will print out the A1 A2 values and also the new L value. Okay, so A1 and A2 and L I am printing out. Okay, and at the end once the loop is over, so this is where the while loop ends. Okay, so when so this loop will continue from here to calculation of the new chi-square and changing the L up to that till I have achieved this particular accuracy which I am demanding here. So that is the sum of the D elements has to go which to be less than 0.01. Okay, so once I have done that, I will print out this value and the chi-square and the standard error, and then I exit. So that's what we will be seeing here. Okay, so I compile this program here and then I run this. So it is waiting for some initial value. So I give some initial value. Let me give that as some minus 0.5 and 0.8 or something. Okay. Okay. So that see this particular case that doesn't seem to work because this didn't go into any. It didn't converge at all. It just blew up this whole program. Okay. So we'll have to give some another initial value. So minus 0.5 minus 0.2. So this seems to converge. Okay, so again this program doesn't seem to converge for all values, so that's something which we should be discussing in the next section. So why doesn't the program converge? So we'll discuss that in the next section. Okay, so now here this particular value it did converge. Okay, and then it went to values called minus 0.186 and minus 1.132. So the A1 A2 values I obtained. And I got a pretty reasonable chi-square and a reasonable standard error. Okay, and now you can see that if you look at the L values have gone to 0 because it was converging. Okay, and if it wasn't, then it would have just blown up to some large number, and then the program would eventually exit because numbers has gone to large. So now we could do this program here because we had used only 2 parameters. Okay, so the 2 parameters was easy to implement because we could actually compute the inverse by hand. So, but now let's say we have a function with a larger number of parameters, n parameters, and then how do we solve this? So we need to have a method to solve. So now in this program, I need to put in something here. So I have computed here the inverse of the matrix by hand. But here I need now a program, a function, which would tell me what the inverse of the matrix is, or what is the solution of this equation is. That is my set of linear equations, which I obtained by finding the derivatives of the Taylor expansion with respect to A. So what the solution of that equation is, I need a function to do that, and then I would call that function from here. That's what I would need to do. So that's what we would see in the next section, and then we will see what case we can get the solution of that and where such an equation could fail. That's what we should look at. So in short, we could have a set of linear equations like this. Okay, so we could have some many parameters. So let's say now this x1, x2, x3 are unknown. So the xn unknowns, and a1, a1, 2, a1, and here are coefficients. And now I need to solve the set of linear equations. Okay, so now in 1 or 2 classes we will discuss in detail how do we go about solving such an equation numerically. That is, we have n equations and we have n unknowns, linear. Okay, and now we want to solve this linear equation. So you can see that if I write it in this form, which we in the previous case in the problem of minimizing the chi-squared or fitting a nonlinear function to a set of data, we would get by finding the derivative of the Taylor expansion of the chi-square. Or in general, we could have a set of linear equations and you want to solve them. There are many such situations where this kind of a problem arises. One example being which is what we just now saw. Okay. So, our idea would be that to develop an algorithm for solving a set of linear equations like this and then put that back into our equation for finding the parameters of a nonlinear function for more than 2 parameters. We should put this, incorporate this program into that function and get a general program for either minimizing a set of nonlinear equations or fitting a set of a nonlinear function of many parameters into a set of data points. So, here is the matrix for that, and then we have this linear set of linear equations, and we can write this linear equations in a matrix form, right. So, we write this in a matrix form. So, that is the first step, okay, to identify. It is simple to see that we have a set of linear equations like this, and I can simply write this as A11, a matrix which contains A11, A12, A1n, A21, A22, A2n, etc. up to AN1, AN2, ANn, multiplied by the column vector x1, x2, x3, extra x1, x2, x3 up to xn, which gives you b1, b2, b3, bn as the column vector. So, that is what we have here. Okay. So, now we have to invert this matrix and then we multiply both sides of the equation by the inverse of this matrix A, okay, then we would get the solution A. So, that is what so basically the idea would be either to find the inverse of this matrix or some way solve this equation. Okay. So that is what we will do. So, the first way to do that is the simplest way is to use a very simple elimination method. We actually saw that already in our function minimization, sorry, in our data fitting the data of the function, which we actually saw when we were doing this for a set of linear equations. In the case of fitting a set of data, fitting a function through a set of data points, we saw this elimination method in practice. Okay. So, here we will do that in a general case. What I mean by that is, if you look at this matrix equation, okay, and if I can make this into a upper diagonal matrix, okay, so that is all the diagonal element, all the elements below the diagonal matrix. If I could make this diagonal, all the elements below this diagonal matrix to 0 without changing the value without changing this equations, okay, or altering this equation without changing its result, right. If I could do that, and then I can see that if I have only this elements non-zero, only the upper diagonal element is non-zero, and then the last equation would simply read ANn into xn equal to Bn, because everything to the left of that will be 0, right. So, the last equation will be simply ANn xn equal to Bn, and then I could solve xn as Bn by ANn. So, if I had a matrix here which has only the upper diagonal elements and none below the diagonal element, then the last equation will be simply ANn xn equal to Bn, and that means xn equal to Bn by An. Once I have obtained xn, then I can go back to the equation above that, which will have An minus 1, An minus 1, and then An minus 1 n, and that equation will contain xn minus 1 and xn, right. But I know xn already, so I can solve for that. Okay. So, that is called back substitution. Okay. So, if you could make this matrix such that all the elements below its diagonal elements are 0, then I could solve it from the bottom, that is by back substitution I can solve for all the x values. So, that is the idea of a simple elimination scheme, okay, and that relies on the fact that if we multiply or divide any row by a number, okay, the equation does not change, the solution of the equation does not change. That is, if I could divide any row by a number, multiply or divide any row by a number, the solution of the equations do not change. Okay. Or if you exchange the rows on either side of the equation. Okay. So, there are many things, there are 3 things which we can do. We can either multiply and divide each row by a number, okay, or we could exchange rows, okay, on either side, on the right and left hand side of the equation, That is just simply making the first equation to the nth equation or n minus 1th equation to the n minus 2 equation, etc. Okay, so we are just shifting the equations, so that will not change the solution. We know that, right? And we also know that we have an equation, f of x equal to a. Then if I multiply up either side by a number, it's not going to change the solution. So that is another. That's the first thing. Okay. Or we could replace one of the equations by linear combinations of other equations. Okay, so that's next method. What we do, take one of the equations, okay, and replace it by a linear combination of the equations. Okay, that will also not change the solution. Okay, so that's the idea here. So that's been summarized here in terms of what happens to each of the elements. Okay. So these operations, that is multiply, divide by a number, or exchange each rows by on either side of the equation, or replace one of the equations by a linear combination of the equations, that's what we're going to implement in this thing. Okay. So what I mean is that what I'm going to say that is, let's look at the equation again. Okay. See, if I look at this equation, okay, now if I want to make this element 0, okay, this particular element 0, what I could do is I could take this, I could subtract from this row, okay, right? I could subtract from this whole row of this row, okay, this particular row divided by the first element and multiplied by this element. That's what I'm trying to say is, if I take this row and divide this row by a11, so every element in this row gets divided by a11, okay, b1 also gets divided by a11. That does not change my equation, right? That does not change the solution of my equation. So I could take this first row of the matrix and divide it by the first element of that matrix. Okay, and that will not change my equation. And then I multiply that by this a21. Okay, now I divide by this row by a11, and I multiply it by a21. So what will happen is this will become a21, right? And then I subtract from this element, from this row, this row. So if I subtract, if I do a linear combination of the rows, okay, the solution does not change. We know that, right? So the linear combination of this row, the row 1 and row 2. So I replace row 2 by a linear combination of row 1 and row 2. Okay. By that, what I do is I take the row 2 and replace it by row 2 plus a constant multiplied by row 1. And what is that constant? That constant is a21 by a11. So I take a21, the whole row, a2, a21, a2 up to a2n, and subtract from that this row a11 up to a1n, multiplied by a21 and divided by a11. So all elements of this row multiplied by a21 divided by a11 subtracted from this will give me a 0 here, and all these elements will change. So I replace this row by a linear combination of these two, and I continue for the next row. Next row again I will do that. So the factor which I have to multiply will now become a31 by a11, and then I subtract from this. So then this will become 0, and by this procedure I could make all the elements below this a11 go to 0. Okay. And then I could repeat this process for the next element, a22. So I could make them again go to 0. Okay, that's the idea of elimination method. So that's what we have done here. So J here is the row index and I is the column index. So the first element would be j equal to 1 and I going from 1 to n, or 0 to n minus 1. So let's stick to this index at 1 to n as the way we mark the columns. In the program it would actually go from 0 to n minus 1. So a.j.i, so a11 is the first element and a12 is the second element of the first row. So j is the row index and I is the column index. Remember this always. J is the row index and I is the column index. So what I'm doing here is, now I take AJI, okay, for the first step, okay, I'll take all j's, okay, which are below the first row, all columns, and I subtract from that and replace that row by, for each element of the row, that's I going from 1 to n. I going from 1 to n, for all j greater than 1, I do this operation. That is, I take AJI and subtract from that aj1, that is the element of the row above that in the corresponding column, and then multiply it by a1I and subtract it by a11. Okay, so a1I is the element in the first row in the column I, okay, and you divide it by a11, that is the first element, and multiply it by aj1, that is the first element of that column j. Okay. By this procedure you can see that if for I equal to 1, for any j, okay, I equal to 1, this would mean that aj1 will go to 0. So that will happen for all rows below 1. That's what I just showed you before. Okay. And the similar thing has to be done on the right hand side too, because otherwise equations would change. To prevent the equations from changing, so we would the solutions from changing, then we have to also do on the right hand side. That's exactly the same operation is done on the right hand side. That is, from we subtract from the bj for all j values greater than 1, aj1 by a11 into b1. I hope this process is clear. That is what we are doing is we are taking the first step, we are making the first column below the first row to be 0. All the elements of the first column below the first row goes to 0. Okay, that's what this step would do. Okay, I guess this is clear. For j greater than 1, j is the row index. For all j greater than 1, all elements I, you subtract from that the first row, okay, the first row, that is a1 ji, the elements of the first row multiplied by aj1 by a11. In this process I could make all the row elements 0. Now I could do this for the next element in this way. Okay, so that is, instead of now 1 I go to 2, okay, and then now I will start from the second element, right, so because the first element of the second row is already 0. So now I do the second element and I go down all the elements. And that process I will eliminate all the thing into second row into 0. So in this, if I continue this process, okay, I can make all the elements below the diagonal to 0. Okay, a simple elimination scheme. Okay, so that's what we are doing. So we take the first row, divide the elements by its first element, that's the diagonal elements, and the second time, say the second step, we will do the second diagonal element divided by second diagonal element. The second row is divided by its diagonal element and multiply it by the element below, okay, that is the j greater than 2. This has been done for j greater than 2, the element below, and then subtract it from the column. Okay, so let me summarize that here. So what we will be doing is, so first once we make all of them 0, and then we come to this one, and then we will take this column, okay, and divide it by a22, multiply it by a31 and subtract from this. Okay, now this will go to 0, this will go to 0, etc. Okay, so once we have done that, we have a diagonal matrix. Okay, and then so in general that's what we will do as this as a subtraction for all elements, and then we have a upper diagonal matrix. Okay, now as we can see that this procedure will not work if any of these diagonal elements go to 0. Okay, so that is one example of where it is bound to fail. In this process of elimination, if any of the diagonal elements go to 0, okay, then we will not get a solution to this, means this will blow up, okay, and we will not be able to work with this. So already there is an if there, that we have to make sure that diagonal elements are not 0. Okay, so if you succeed in doing this without any diagonal elements going to 0, and then we have a matrix like this, in set of equations like this, that is, the matrix would be, you can see the corresponding matrix for this would be 0 below the diagonal and non-zero above the diagonal. Okay, now you have this equation. Now you can see, as I said before, we can solve this equation here. Xn has Bn minus 1 divided by An, Bn divided by An. Now this upper index here to show that this has been changed n minus 1 times, right? Each time we do an elimination, okay, all the elements below that particular row gets changed. So the last row gets changed n minus 1 times by this elimination process. That's what I mean by this index here. So this 1 is this changed once, and this will be changed n minus 1 times. So similarly on the right hand side too. Okay. So now we can solve this equation by back substitution. As I said, you can see from the previous one that xn is Bn by Ann. Okay, similarly xn minus 1 is now Bn minus 1 minus An minus 1 and xn by An minus 1 n minus 1, so elements. So, but now we know xn from this previous solution, so we can substitute that back here. So, we can write a general formula for this, okay, and as xk is equal to bk k minus 1 minus sum over j going from 0 to n akj k minus 1 xj by ak. So, we can do this by, we have to start from k equal to n. Okay, so we can do this solution starting from the bottom. Okay, so again, will it always work? Obviously not when you have the diagonal elements going to 0. Okay, so we will see an implementation of this thing for one of the, let's take a matrix, a set of equations like this, okay, and then we could solve this equation and see what the solutions we get. So this is also a very special equation, that's why been shown here, that this equation, this whole process will also not work if one of the diagonal elements are equals to very small value. Okay, so that is also a process. In the elimination process, we may not make any element 0, the diagonal element, but the diagonal element could go to very small value, okay, compared to other elements in the row. Okay. So we could have other elements in the row very large, but one of the diagonal element could be very small. Okay, in that case, also we'll have a lot of errors. We'll still get a solution, but the solution could be very errorless. So we could have a lot of errors in the problem, and that kind of matrices called ill-conditioned matrices. And if you cannot eliminate that, okay, there are ways of eliminating such situations, that is diagonal elements going to very small value, but we will discuss that a little later. First, let's see the implementation of what we have discussed so far, that is simple elimination scheme, and to solve this equation. So that's what we would just look at now. So we have a program here which would do that job. Okay, so we have a 3 by 3 matrix, right? So we have three unknowns x1, x2, x3, and we have 3 linear equations. So we have a 3 by 3 matrix. Okay, so 3, 1, 4, 6, 2, 1, 1, 4, 2 is the elements of the matrix. Okay, so that's what I put in here. 3, 2, 1, 6, okay, 6, 2, 1 and 1, 4, 2 are the elements of my matrix. There's a 3 by 3 matrix. Okay, and the right hand side is 7.65, 13.5 and 16. So that's what this equation is. Okay, so that this equation is what I'm trying to solve. Okay, so we have that equations here, and I'm just printing out the matrix here, so that you can see the matrix in the matrix form. Okay, and then I do the elimination scheme here. So now here is where I'm starting the elimination scheme. Okay, so remember I go from index k to 0 to n. Okay, so that is n now in my case is 2. Okay, because this is program which goes from 0 to n minus 1. So n is 2 here. Right? So there are 3 by 3, so it goes from 0 to 2, so I take all the rows. Okay, so I take the first row here, that's 0, the first iteration. In the elimination, I will have 3 rounds to do. The first round I go 0, and then I take, so whatever the k value is, I start the elimination. I have to make all the rows which are below this, right, below this to 0. All the elements of that column, okay, go to 0. So if it is 0, and then all elements of the 0th column which are below this k should go to 0. That is below k means k plus 1 onwards. I want to make them to 0. Okay, so I define this djk by dkk. So I take the diagonal elements of that particular k value for the k row, the kth row. So I take the kth row and I take all the rows below the kth row. Okay, and my idea is to make all the columns all the elements in the column, the kth column go to 0. Okay, all the elements of the kth column below the kth row should go to 0. So this is the elimination process. So I have defined a parameter x here, which would be djk divided by dkk. Okay, so I'm doing exactly what is here. Okay, so my idea is to do this. Okay, so I'm doing that process here. So I have the djk divided by dkk, which we have what we call djl divided by all. Okay, ajl by all. This is A is a matrix here, and D is the matrix in this program. Okay, So that's what it is here, okay, and then I multiply dki, okay, that is the whole elements of that row by this quantity, and subtract it from my present value, the whole element, all elements of the jth row, okay. So, right. So what you can see, x into dki would simply mean that I take the ith column element of the kth row, right, multiply it by djk, that is the element, the jth row's kth column element, okay, that is what it is, okay. So and I would subtract it from this one. So I am changing the jth row, all the elements of the jth row by this process, okay. And you can see that when I equal to k, okay, this will go to 0. Okay. For I equal to k, this will go to 0, because it will be djk minus djk divided by dkk into dkk, okay, right. So this will be, x will be, for the I equal to k, for this x would be simply djk divided by dkk into dkj, so that will go to 0. Okay, so that's the idea. And then I would have to change the right hand side of the equation also. Then I will print out that matrix. For every step I will print out this matrix, okay, just to see that how each column by column, how do I change this thing, okay. So once I have all the matrix elements gone to 0, okay, below the column gone to 0, so we will see that first here. Okay, so let's look at this then column by column, okay. So this is the 3 iterations which I do. Since I have 3 by 3 matrix, I have 3 iterations, okay. So the first iteration, you can see that the elements below the first row has gone to 0, okay, and the second iteration, the element below the second row has gone to 0, okay, and the third iteration, I have the element below the third row gone to 0. So that's the procedure which I will do. Okay, so sorry. So now this is the procedure. So by this process I have kept now this is only a 3 by 3 matrix. So I already have here an upper diagonal matrix. Okay, I have upper diagonal matrix, and all the elements below that are 0. Okay, so there's only 2 to do here. So upper diagonal matrix, and I have only the elements of the diagonal and the upper diagonal elements being non-zero. And similarly, I would make the changes on the right hand side also. Okay, right hand, this what is printed here is the right hand side of my linear equation. Okay, and then I do a back substitution, and I get the solutions of this form. Okay, and I'm just showing that if I substitute the solutions back into the equation, okay, I am getting the same answers as what I am expected to get. So actually, this is finding the solution of this equation. Okay, so the back substitution is implemented here. Okay, as I go from now starting from bottom, so I start from n to 0. Okay, so I go from n to 0 to find the solutions. Okay, in steps of -1. That's a back substitution, and I am using this formula here which we have. Okay, then I just simply use this formula to get my equations. The general formula written here. Okay, I just to get the formula, and I'll go back. I'll get the solutions here. So that's the idea of the implementation of a simple elimination scheme. Okay, so let's try to summarize what we've done before we go into what all the different problems which can have. Okay, I will try to summarize what we have done. Okay, so in this process, so here it is. So we want to solve, let's say, an equation of this form. Okay, some equation of this form, linear equation, which has x1, x2, x3 as unknowns, and we have three linear equations to solve. Okay, and then what we do, we write these equations in the form of a matrix equation. Okay, so we have these equations can be written in a matrix form. The associated matrix would be this. Right? This multiplied by x1, x2, x3 would give me this solution. Okay, and then I will do this operation, that is I will subtract from this row, okay, this row multiplied by 0.01 divided by 3. Okay, so that will make all of them 0. So that will make all of my elements in the first row, the first column elements below the first row to 0, and then I repeat that so that the matrix would go into this. Okay, then my equations would go into this. Okay. and then I repeat that process again for the second row. Okay, so that would make my equations change to that form, and the equation change to this form, and my matrix change to this form. Okay. Now I can solve for x3 from here, we can see, and then I can substitute that x3 into this and solve for x2, and once I have x2 and x3 I can solve for x1. So that's my back substitution process. Okay. So I guess you get an idea then. So from this I can solve for x3. Okay. So once I have that x3 value, okay, I could just now solve for x2 but from this equation, right? I have an x2 equation, so I know the x3 value, I substitute that here and get the x2 equation. Okay, and then once I have that x1 and x2 and x3, then I take the first equation which has x1, x2 and x3, and I substitute for x2 and x3 and I get the x1 value. So that would be the summary of the process which we just followed. Okay. So there are many cases where it can actually fail. Okay, so that is what has been listed here. Okay, so there are many cases where it can actually fail this equation, this solutions. Okay, so we could have round off errors coming on the way in our multiplication and division, or it could have ill conditioned systems where one of the elements is going to be one of the diagonal elements go to very small value. Whatever we do, we could have one of the elements going to very small value. Okay, so in this kind of situations, we have to be a little more clever and then change the set of equations appropriately, and that's so using some technique called pivoting. Okay, we can actually interchange the rows such that the diagonal elements are always very large, and that's something which we would discuss in the next class.